Hello everyone, my name is Daniel Reimer and I'm going to briefly introduce you to my research, which is investigating how experimentation and simulation can be used hand in hand to optimize the vertical stirred milling process. Vertical milling involves packing a stirred tank with thousands of grinding media beads and then passing through either a powder or, more commonly, a slurry between the voids. Once the mill is switched on, the energy from the impeller causes collisions between the media, hopefully with enough force to break down the particulate material within the slurry. It is important to be able to control the collisions between the media to maximise the number of fruitless collisions and to get the particulate material down to the desired specification size. Although simple in principle, grinding and comminution is a massive concern for the environment. Over 50% of all engineered products are either powders, contain particulate material, or have at least one size reduction step during processing. All these processes mean that the grinding industry contributes approximately 2% of global energy. However, most energy associated with milling is waste as heat and sound. Some processes have even been found to be less than 1% efficient, making the potential for optimization very large. So how is my research tackling this issue? What we are aiming to create is a calibrated model which simulates the behaviour of the milling performance. We are using a coupled approach of two techniques, the discrete element method, DEM, which was invented by Kundal and Strack, and concerns the motion and interactions of the grinding media beads, and computational fluid dynamics, CFD, to simulate the slurry phase, and that is a derivation of the Navier-Stokes equation. The particulate material is assumed to be part of the CFD fluid, as the individual particles are simply too small to model discretely. To calibrate computation with reality, particle data was collected using the Positron Emission Particle Tracking method, or PEPT for short. A radioactive tracer is placed into the mill, shown here in red, and that emits positrons that are detected by a pair of parallel scanners. The location of the detections can be extrapolated using algorithm to trace back to the position of the particle. Taking repeated samples over a period of time lets the researcher build a picture of the full motion of the particle within different planes. This is shown on the right-hand side here. In the PEPT experiments, different viscosities of silicon oil were tested at different impeller rotational speeds to gather calibration of data that was then used for simulation. Approximately 1 kilogram of 4 millimeter glass beads were used as the media, with one of these being radiated as the tracer each time. Data was gathered for 2 hours in each run so that enough samples could be collected. PEPT is able to report a number of different output parameters that can act as field maps for the simulations to then try and replicate, but can also act as standalone results. These show that the media particles were able to reach the entire active milling space within the time period of each experiment, indicating that the system has good mixing. This is improved as rotational speeds increased, as more energy is being supplied to the mill, and the equivalent velocity profiles also show that the fastest motion is around the impeller tip, as this is again where the energy is greatest. Early simulations show that there is a level of agreement between virtual and reality, but there is potential to change the media and fluid parameters to further improve the level of agreement. These findings are currently preliminary, but show great promise that a computer model which shows full likeness with milling equipment is achievable. The future study will refine the level of accuracy within these initial results and look to create a series of assumptions that can maintain the result without reducing the computational expense, something which is highly important within the industrial setting. Thank you for watching, and a special thank you to all of those who have contributed to the project.